We present a 6 degree of freedom active rigid body stabilization method using a parallel manipulator, and we propose its possible applications.
So some background. The Stewart platform is a category of parallel manipulators that can orient a mobile platform with 6 degrees of freedom. There hasn't been much research on topics besides open-loop control systems, like flight simulators or satellite dispositioning. So traditionally, Stewart platforms are built with high-precision extensible linear actuators, but these designs are typically more expensive.
Here we demonstrate each individual axis of our Stewart platform. This is a picture of our CAD model we used. The sway axis, if you imagine a boat moving on water, the sway axis is basically the movement along the x-axis. Surge is moving along the y-axis. So, in reference to like the table frame, this would be the xy would be on the table frame, and then heave is moving along the z-axis. Roll is rotation around the y-axis. Pitch is rotation around the x-axis. And yaw would be rotation around the z-axis. And now you can see what happens when two of these motions are combined. So in orbit, you can see that the roll and pitch axes are moving together. And here you can see that the heave, roll, and pitch axes are all moving together.
So a problem and rationale. So traditional camera stabilization in the film industry is limited to 3 axes of rotation. So a 6 DOF active stabilizer would allow for sway, surge, and heave control in addition to yaw, pitch, and roll. So in the film industry, a stabilized platform would reduce the effects of shaky hands as well as improve shots taken while walking.
Another proposed application would be to mount such IMU stabilized Stewart platform to boats. So you could have a Stewart platform under a stove. So you could cook while you're at sea, and whatever you're cooking, your pots and pans wouldn't fall off if the boat sways. And another application for boating would be to mount a Stewart platform to a bed, so people who get easily nauseous at sea could actually go out and sea.
So the design and fabrication. So all parts were chosen to be easily accessible, and all the hardware and electronics were sourced from Amazon. So the CAD model was designed in SolidWorks, and the 3D printed parts were designed to all fit within a 100mm by 100mm print bed, which is the most common size, since it's very easy to get a printer with a bed that size, since it's like hobby grade. And after that, larger components like the mobile platform were designed to print in multiple pieces and be assembled together.
In the spirit of keeping things as simple and as inexpensive as possible, we decided to use the Arduino system of microcontrollers, and these can process the IMU inputs as well as output servo commands. Now for the wiring, we decided to keep things as simple as possible as well. So we didn't solder any of the wires to the Arduino, so we just stuck with the stock JST jumper pins. Now the wiring doesn't look too good, but it can be improved in the future with smaller microcontrollers and soldered connections.
So the IMU. So to keep costs low, we use the most common Arduino, and the IMU is the MPU 6050. So the MPU 6050 measures linear accelerations as well as rotational velocities, and the IMU was mounted on the mobile platform at a 60-degree angle to the servo F of A plane.
Here you can see the Stewart platform moving with IMU correction. For the roll and pitch axes, you can see that the servo springs back when the base platform is moved by hand. You can also see that the mobile platform isn't able to keep at a parallel position to the table, because we are using rotational velocities and not rotational position. For the yaw axis, you can see that the mobile platform is correcting itself, similar to how a spring would. Heave, if I move the platform up and down, you can see that the mobile platform corrects for this motion as well. And sway and surge, it's really better to look at it from overhead. You can see that as I move the base around the table plane, the top platform is trying to keep at a minimal acceleration. And when all the corrections are activated, you can see that as the super platform is moved around, the mobile platform is able to keep at a relatively balanced state. Thanks for watching.